Hi everybody. In part 3 of our Electronics 101 and a half series, we're going to look at the power transformer. And we're actually going to kind of get more into detail of what a transformer is and what it does. So if that sounds interesting to you, stay tuned. That's what we're going to do. Now, looking at the diagram of our little amplifier kit that we're going to be building, we're going to be interested in this portion down here. Of course, starting any amplifier project, at least for me, it's different for everybody, but at least for me personally, I like to start by building the power supply first. And I test the power supply after I build it, make sure everything's working, and then and only then will I move on to build the rest of the amplifier circuit. But the first part of a power supply is going to be the transformer. And what is a transformer? Why do we even need one? Well, amplifiers, just by their nature, in any circuit for the most part, many circuits I should say, not any circuit, but many of them, require different voltages. They don't use just one voltage. And even the ones that only use one voltage will most likely not use the voltage that's coming out of the mains power of your house or wherever you are. So when you plug into your mains outlet, you're going to, depending where you live in the world, you're going to either have a 120 volts AC RMS, as we talked about in our last video series, or we're going to have 240 volts, 230 volts, 100 volts, whatever. The point is, it is only one voltage. And the other strange thing is most of our circuits, including this circuit here, require DC voltage. But the voltage coming out of your AC mains is AC. It's alternating current. So not only do we have to change that voltage into direct current, but we also have to change it from one voltage, that mains voltage, whether it's 120 or 240 or whatever, into the voltage that we need. In this case, vacuum tubes require higher voltage than our mains voltage. Some of them require a lot higher voltage. This one is only running a maximum of about 278 volts if you look here. But that's still a lot higher than my 120 volts that I have. And it's even higher than 240 volts. But also, vacuum tubes have filaments, and those filaments actually need much lower voltage than our mains. If we connected the mains directly to the filament of our vacuum tubes, the filament would go away really quickly. You really only need 6.3 or 12.6 volts going into the filaments of the tubes. So as you can see, we need many different voltages. Now our first question is, why is it AC voltage? When what we're using is DC voltage, why do we have AC voltage coming out of our mains? Well, the reason is because of these devices right here, transformers. A transformer has to have AC voltage in order to operate. And this transformer is capable of changing our mains voltage into a different voltage. All right, we'll get more into that in a little bit. Now, it works by changing one type of AC voltage into another level of AC voltage. It does not work with DC voltage. Now, is there some other way that we can just change DC voltage into another DC voltage? Well, yes, but those ways can get very expensive and require a lot of circuitry, although in today's day and age, that's getting less and less of an issue. But in addition to that, most of the simple ways of changing DC voltage around are very inefficient. If you take into consideration what we're doing right here, for instance, we have 278 volts here, but we need to drop it down to about 172 volts up here. we're running it through resistors. So you see there's a resistor here and a resistor here, and we learned from our last video that resistors convert energy into heat, electrical energy into heat energy. So really we're wasting a lot of our energy here turning it into heat on these resistors. Now in this particular case, we don't need a lot of energy. Even though we're dropping a lot of voltage, the current is very low, so it's not terrible, but it's still inefficient. If we had to take large amounts of energy and drop it down and still have a large amount of energy at a lower voltage to feed a circuit, we would be creating a lot of heat and wasting a lot of energy. Transformers, however, can transfer that energy fairly efficiently. There's a little bit of loss in the way that a transformer works, but for the most part, it does a very good job of taking the amount of energy here and preserving it over here while still changing the voltage around. So we're going to look at that right now. We're going to look at some diagrams of what a transformer is and how it works. Now here's just a simplified schematic symbol of a transformer. So if we look at a schematic diagram, this is the symbol that you will see that represents a power transformer, something like this, or even a small transformer like this. This line in the middle represents the core of the transformer, and every transformer that you're going to be seeing for this application anyway has a core made of steel or iron or ferrous plates, and you can see these laminated plates in here. More about that later. It also has these little squiggly lines, and those represent a coil of wire that is wound around this iron core. So if we look on this transformer, you can actually see the windings. So you see that little wire, and it goes down in here and it wraps around and around, and this core is actually, there's a piece going down the middle that's just like these side ends. So you have one pole going down here, one going through the middle, and one going down this side, and they're all connected. All right, and you have this winding down here is the input winding called the primary, and this one here is the secondary winding that would be on this side. Now this is a different transformer than this schematic is drawing, because this one only has one secondary winding on here, whereas you can see this one has two. So let's look at a little more detail of this. The transformer that we have here has two primaries, and each one of them is designed to have 110 volts input, nominal. Now you can run this up to 120 volts and it won't hurt it, okay, but they're just, the measurement point that they're using is taking into consideration that you're putting 110 volts in. They call it that because that's, saying 110 is kind of like saying North American style mains power, although that 110 can be 115, 117, 120, or 125 volts. They're all kind of clumped in with this 110 volt thing. And the cool thing about this transformer is we can wire it this way. You see these two are wired in parallel. So the two tops of these windings are connected together and the two bottoms are connected together. And each one can take that 120 volts or 110 volts. And since they're wired in parallel, the two wires double up. So you can handle twice the amount of current. Now that's going to be important in a minute, and we'll find out why later on in this video. Or we could remove this wire, and we can remove this wire, and we can connect here to here, and that would put these two coils in series. And now the voltages add up. So I could put our 240 volts from this side up to this side, and the path will be this way, and we can operate this in Europe, for instance, on European mains, which would be 230 or 240 volts. This transformer also has two secondaries. One is called a step up and one is called a step down, and we're going to learn about that as well. Now for this video I did a couple of drawings and they're pretty rudimentary, but it's as much as I could do with Paint Shop. I'm just using paint and doing it real quick because I really don't have a lot of time to get into too much detail, and I don't like copying a lot of things from online. So anyway, these are two different styles of transformer. One of them, if you see, is called the step up transformer, and the other one is called a step down transformer. They both work on the same principle in that you have this steel or metal core, and this type of metal can magnetize. It's magnetic, and there's some special properties about this that we're going to have to talk about later in the video, and that'll be the half part of Electronics 101 and a half. We're not going to worry about that right now. Just understand that this carries a magnetic field, and the way this transformer works is it converts an electrical field or an electrical current into a magnetic field. So a lot of us, when we were very young, we did the little experiment where we took an iron nail or a piece of metal and we wound a piece of wire around it and we connected it to a battery, and it turned that metal nail into a magnet. Well, this works on a very similar property. It converts an electrical current into a magnetic field on this core. That magnetic field then couples to this other coil, and then the magnetic field creates an electrical current on this coil. Now, here's the trick to it though, and this is why we use AC and not DC. This type of transformer cannot work with DC, with direct current. It has to have alternating current. And the reason for that, I should say, it has to have changing current. The only time that you will get energy to transfer from this coil to this coil, because they're not electrically coupled. See that? In no place do these wires touch one another. These wires are insulated. They're not even touching this metal core. They're actually insulated from this metal core. In the real world, if you notice, this transformer has a little plastic bobbin, and that bobbin insulates electrically those little enameled wires from the core. So at nowhere does it electrically touch. However, the way this works is anytime there is a changing magnetic field, as that magnetic field builds and then collapses, it will also induce a current through this coil. Through that magnetic field, it will also cause an electrical current to build and collapse. Once that happens, once you have it's at a resting state, no matter how magnetized or demagnetized this core is, you will no longer have the voltage going from this side to this side. So you have to have a changing magnetic field for these to work. Now this is all based upon Faraday's law and the Maxwell-Faraday equation. And these are things you can look up yourself online. There are many, many good websites that talk about Michael Faraday and the work that he did with inductance. So look that up and you can understand how that works. But the main thing I want to take away from this Electronics 101 is you have to have AC in order for a transformer to work. Now, a cool property of this transformer is that if you take the number of windings and you count how many times this wire wraps around the core, and then you look at and this is called the primary winding. The primary is your input. And if you compare that to the output, which is called your secondary winding, and you count the number of turns, there's actually a correlation between those number of turns, and we call that the turns ratio. When you have less turns on the primary, the input where you're connecting your mains, and you have more turns on the output, what's going to happen is you're going to have the voltage is going to be increased. It's going to step the voltage up. And it steps it up based on that ratio. So for instance, if I have one turn here and I have 10 turns on this side, if I put 1 volt on this side, I'll get 10 volts on this side. So as long as the ratio, and the same thing, if I have 10 turns on this side and 100 turns on this side, and I still put only 1 volt here, I'll still get 10 volts out here. Does that make sense? So this is a step up. Step down transformers work exactly the opposite. If I have 100 turns here and I have 10 turns here, and I put 10 volts on this side, I will only get 1 volt out here. It's always going to keep that same ratio. Now, of course, this has to do with just the transformer that we're talking about, these power transformers that you see on your stereos or in a linear power supply or something like that. When you start getting into other transformers with different types of cores and different frequencies and different phase relationships, all of that changes, okay? But for what we're talking about in this video, that's how this works. Now, it is possible to have a transformer that has step up and step down at the same time. If we take a primary winding, let's say it's set for our 120 volts, so we put 120 turns here. That's not exactly what they do though, but we're just, for sake of simplicity, and that's going to be our input. We can have one winding with a whole bunch of turns to step the voltage up, and we can have another winding with fewer turns to step the voltage down at the same time. And this one circuit will drive both of them. And that's really what we were seeing in our little power supply transformer for our vacuum tube amplifier. So we have a single primary input, and it's wired for 120 volts or 110, whatever they're saying here. And we have one winding that has a whole bunch of turns that steps the voltage up. And then we have another winding with very few turns that steps the voltage down. But the difference is this one is going to be a lower amount of current than this one. These windings are going to be very thin wire, very fine wire. And these windings are going to be very thick windings and wire. And if we look at this, we may be able to see it. So right here, this yellow wire, and let me put this down and let's see if we can focus the camera on it a little bit. I don't know how close I can get without it going blurry on me, but there we go, that's pretty close. If we look at this yellow and black wire, that represents this winding right here. This is for the filaments of the vacuum tubes, and filaments take a whole lot of current at low voltage. So if you look at the wire here, it's very hard to see, but if you look right here next to this yellow wire, do you see that copper enameled wire there? It's a very thick wire, and it's designed to handle a lot of current. So it has few turns with thicker wire. And if we go to this side, you can see there's multiple windings, and the innermost windings, those are your primary windings. And that's this red and black wires. There's two sets of them. Two sets of black wires, two sets of red wires. Those represent these ones right here. You know, for these two. And you can see they go in here, and you can physically see that is a thinner diameter wire than the filaments. And then if we look next to that, we have this winding. You can just barely see a couple turns of it right here. It's very fine wire, and it's a lot more turns, and that represents this green wire, these two green wires, which is your high voltage. So this is your step up winding. Let me back the camera out. This is your step up winding. This is your step down winding, and you can even see the connection leads. Actually, these are thinner wires. These are thicker wires to handle the more current. These ones handle lower current, but will have higher voltage. Everything's ratios, and we're going to learn about that here next. And then these are our primary, and of course, if we wire the two black wires together and the two red wires together, that puts those two primary windings in parallel, just like we have on our schematic. If we wanted to wire them in series, I would take one of the red wires and disconnect it and connect it to one of the black wires like this. And they would be connected together, and then the other black wire and the other red wire would be your inputs, if that makes sense. So what we would do is we'd take this black wire from this winding, connect it to this red wire from this winding, and they would be tied together. And then these two wires right here, this one and this one, would be your 230 volts or 240 volts input. They would be wired in series. Now this green and yellow wire is connected to the core, and if we look at the original drawing, our big drawing of our schematic, you can see there's this little symbol. That's the ground symbol. So this ties to the chassis, and what that does is that makes this whole laminated core, it turns it into it grounds it. So this actually acts as kind of a shield. So again, none of these wires are going to be tied to ground through this wire, because they're all electrically isolated from the core because of that plastic bobbin that everything's wound around. But what this will do is this will allow the transformer to kind of act like its own little noise shield. Very cool. And if you look, they always put, on this one at least, they put a little map showing you each winding and what they represent. Now here's an important rule to remember when using a power transformer. As we said, we have step up and step down, and we have some that are combination that'll step up and step down at the same time. I could take this coil and wind it on top of this coil, and I could have that step up and step down at the same time. Here's the problem. Remember the law of conservation of energy. Energy cannot be created or destroyed. It can only be transformed from one type to another. So we can't make free energy. All we could do is lose some energy by converting it into another type of energy that we don't want. And that's what happens inside this core here. This iron core, okay, it will, whenever it doesn't want to change. It's happy the way it is. And when you try to magnetize or demagnetize it, you have something called eddy currents, and we'll get more into that maybe at the end of this video. I'm going to do a last part of the video that's going to be the 1/2 part of Electronics 101 1/2. And we'll talk about eddy currents, and we'll talk about lamination of the cores and different core materials. But understand that because of the way this thing works, this magnetic object here, this metal, will try to oppose those changes in magnetic field, and you'll lose a little bit of energy in that process by turning it into heat and so forth. So a transformer isn't 100% efficient, but it's very, very efficient, believe it or not. Which leads us to this little terrible drawing of mine that I did on paint. But I want to try to give you an idea of how we have to pick our transformer. The big thing is, think of this as a balance. We don't want the balance to tilt one way or the other, do we? We want it to stay balanced. And in order for it to stay balanced, the amount of power that you need to get from your secondary, all of your secondary windings combined, it has to be equal to the amount of power that you're feeding into it. Now, what is power? Power is measured in a unit called watts. And watts is the product of voltage times amperage. So your volts times amps equals your watts. It's very simple Ohm's law stuff. And the main thing we need to remember is no matter if it's a step-down transformer or a step-up transformer or even a combination of the two, however many volts and amps are coming out of here, we have to times that all together and come up with a number of watts. And we know that then this winding has to provide that amount of watts. So whatever we feed into this coil is going to have that many watts. So for instance, if I need 1 volt at 5 amps, so it's going to be a low voltage, high current power supply that we're driving, I have 5 volts going into it, and we're talking AC, of course, remember. I will only need 1 amp to feed this, because 5 volts times 1 amp equals 5 watts. And 1 volt at 5 amps equals 5 watts. So they balance. If I change the voltage or the amperage here, I have to change, if my voltage will be fixed because of your mains input, I will have to increase or decrease the current in order to make it balanced again. Same thing on this side. If I have 5 volts at 1 amp, this is a step-up transformer, and my load draws 1 amp at that 5 volts, and I only have 1 volt feeding the transformer, I will need 5 amps of current in order to provide that 5 watts that this thing needs. Now, this is an ideal situation. In the real world, as we talked, we're going to lose a little bit of that energy in the process through this core. So really, we need a little more than 5 amps. We may need a little higher amps, not much, but a little bit, to compensate for the loss here. This is all basic transformer things. So what I'm saying is you need to have the transformer that matches the load that it's going to have to drive. Now, if we look on top of this transformer, this is a very simple transformer. It just has a primary and a secondary. And you can see that the primary, they call it 115 volts. And they pick a voltage like this, but the transformer can handle a little bit more. They know that your mains voltage could be 125 volts, so that's 10 volts higher. But what they're saying is if you feed exactly 115 volts into this transformer, it will output exactly 24 volts on its secondary winding from here to here. And if I put 125 volts in and we look at the turns ratio, this will be a little bit higher than 24 volts. And you're going to have to take that into consideration when you build your power supply. But the bigger thing is they have this other thing here called 30 VA. VA stands for volts times amps, which is the same thing as watts. But when we're talking about transformers, we rate them in VA, volt amps. And what they're trying to show you here is you need that combination. We cannot put in or take out more than 30 VA before this transformer will fail. What happens is called saturation. This core of this transformer can only magnetize so much. It can only create so big of a magnetic field, which means it limits the amount of energy it can transfer before it's as magnetized as it can get. We call that saturation, core saturation. So if we look at 30 VA at 24 volts, if I connect a 1 amp load to this that draws 1 amp, I'm already using 24 VA. So I really can't drive this a little much more than 1 amp. Because as soon as we start getting to that VA max, number one, the transformer is going to saturate. Number two, this winding is going to get very, very hot. Because remember, there is loss in this transformer that turns into heat. And those windings are going to get hot because of the current flowing through them. They act just like a resistor, right? They're wire. So that's why these transformers all come with a VA rating. If I wanted a transformer that was 300 VA, which is 10 times bigger than this, and still had the same input and output voltage, you would see that it is a much larger transformer. It would have a much bigger core. It would have thicker wire on the windings to be able to handle the extra current. Conversely, at the input, 115 volts, if you take 115, or if you take 30, which is the VA, and you divide it by 115 volts, it means 260 milliamps is the most current, or close to, remember, that we would ever want to draw out of our mains into this transformer without hitting saturation once again. And if you look, here's your primary windings. You see how much thinner they are? So you see there's the primary, there's the secondary windings are thicker. Again, you really don't want to draw any more than that 260 milliamps on the input of this transformer. And that's how VA ratings work. Remember, it's a balance. Hope that all makes sense. Now let's see how these ratings relate to our amplifier. We have an output on our secondary, and let's get the little schematic back out again. And I'm going to back this up a little bit. So we have an output of our secondary. The high voltage step up is 230 volts. And if I take 230 volts, 230, it says that it can handle a maximum of 200 milliamps, or 0.2 amps. So I times that by 0.2 amps, and I get 46 watts. So this is good for 46 watts. Also, if I look at this secondary, it's rated at 4 amps. So you have 3.15 volts, and remember, this has what's called a center tap. So all they did is halfway through those windings, they connected a wire, which is this black wire, and they connected it to the center. And why they do that, we'll learn later on, especially when we get into designing the whole power supply. But if you measure from the center tap, you'll get, since it's halfway down, you'll get half of the total voltage of the winding. So if you measure from this center, this is from here to here is 6.3 volts. But from here to here is 3.15 volts, and from here to here is 3.15 volts. It's half of the total voltage. So this is 6.3 volts. And it says that these windings can handle 4 amps of current at that 6.3 volts. So if we take 6.3 volts times 4 amps, that's 25.2 watts. So this side is 25.2 watts. So you can see we have a total of 71.2 watts. Now I'm very oversimplifying some of these things, but for the most part, you can see we have a total of 71.2 watts that you have to deliver to this. And it's actually going to be more than that because of our losses and different things. But let's just say 71.2 watts. If I feed 110 volts into here, like they're saying, I take 71.2 watts and I divide that by 110 volts. it means that I need about 647 milliamps if I'm going to drive these windings at their maximum. Now remember, when your amplifier is sitting there, it's not drawing all this full amount of power. But when you're cranking the volume up and you're using the circuit and you're driving it at its max output, you will hit these numbers, or you could come close to it, possibly. Now, or I should say it will be higher. Now, what's a quick way that we can determine if this transformer is sufficient for this circuit or not? Let's look at that. So let's take a look at this. The output tubes by far are the things, along with the filaments, by far are the things that take the most current. Usually your little driver tubes and your phase splitters and everything, and we'll talk about this terminology later in the series, these don't draw a whole lot of power. You're looking at just a couple of watts total for them. But these guys, you have to look at what kind of tubes they are and how they're going to be arranged. Now this is called a push-pull circuit, and we'll look at that. And don't worry, we'll talk about this later in the series. But the tube types are called a 6P1. Now a 6P1, I had a hard time finding a really good data sheet for it. But a 6P1 is very, very similar electrically or electronically to a type 6AQ5 tube. So we're going to look at a data sheet for a 6AQ5. And if we go through here, it shows us a few things. So for instance, the cathode is 6.3 volts. So there's that 6.3 volts we were looking at, right? And each tube draws about 450 milliamps. Now remember, this is a 6AQ5. The 6N1, or the 6P1, I'm sorry, could have a different filament current. There are some differences from one tube to another, even though amplifier-wise they work the same. So let's just say that they each take 500 milliamps. That's just for good measure. So if we have 4 of these tubes, remember this is a stereo amplifier, and that schematic only shows one channel. The other channel's identical. So there's 2 of these amplifiers on this chassis. So I have a total of 4 of those 6P1s. If each one draws a half an amp, that's going to be 4 times 0.5 is going to be 2 amps. Remember, we have a 4 amp maximum winding before it'll overheat. So we're only using about half of that. In addition, those 6F2 tubes, remember we have 2 of those as well. And those will probably each draw a little bit less than that, but they'll be close. They'll also draw, let's say, I'd have to look up the data sheet, but let's say they each draw about 300 milliamps. So I would have 2 more of those, that would be 600 milliamps. So that would be a total of 2.6 amps for the filaments. Well within what this thing can handle. So this transformer is good for the filaments. Now, we also want to see if our high voltage winding, remember it can't go above 46 watts, and it can't go above 200 milliamps. So let's look at what these tubes operate at. Now when we look at a tube data sheet, they have maximum ratings, and the maximum ratings are dependent upon how you connect the amplifier. Now this is not a class A1 amplifier, it's actually a class AB amplifier. And we're going to go down here, it's a class AB1, and the 1 and the 2, don't worry about that, that's a way down the road thing. But the main thing, the maximum signal hour output values for 2 tubes. So that means each channel, if you connect those 2 tubes in push-pull, the way that our schematic is showing right here, the maximum signal power out you would have would be 10 watts. So each channel could theoretically draw 10 watts. Now, that's what the tubes handle for the output section. And remember, we're going to look at another couple of watts used up by the driver tubes and those tubes, and that's going to be lost in the power supply because our resistors are in there and they're converting some of that watts into heat to get us the lower voltages. See, we only want 88 volts here, and we only want 172 here, and we're dropping it down from 278 volts here. So we have some losses. So when you add that all up, let's say you have 10 watts for each channel, so that's 20 watts. And then we have another, let's say 5 watts for the drivers and for the low voltage things. So that's 25 watts. And if you recall, the maximum that we could put on that winding for the high voltage is 46 watts. So this is almost double what we need, which is what you want. You never want to run a power transformer near its maximum rating. You want it to be, ultimately it would be nice to have it at about half of where it should be. That's how I like it. Now again, there are rules that people will use, but for me, this transformer will run relatively cool if you're running it at about half of its rated power. If you run a transformer closer to its rated power, for instance, that Fisher 500 that I did the video on, that was a mono amp, it was a pretty powerful amplifier. That power transformer runs close to its maximum capability, and as a result, that transformer, after a couple hours of operation, that core will really begin to heat up, and you can actually feel it when you touch it. It's hot. It gets hot to the touch. This one probably will not get quite as hot. So it's a good choice of a transformer, and that's what we need. So that concludes the basics of how a power transformer works. For the rest of this video, I'm going to just do a little bit more to get into a little bit, but not a whole ton of detail of the properties of a transformer and some of the more detailed things about how they work. Now, I mentioned the term eddy currents a little bit back in the video. Let's talk about that for a second. Whenever we take a metal bar, let's pretend this little tongue depressor is a metal bar. And if I pass a magnetic field, if I induce a magnetic field that's going this direction, north and south, not only will there be the magnetic flux moving this way, but if we look at it from the end, there will be another opposing magnetic field going in this direction, kind of like in a circular pattern. Kind of like an eddy current in the ocean with the waves. And that eddy current will oppose the motion of this magnetic field. Now, the bigger and thicker the piece of metal, the greater the eddy current will be. But we have a way to get around that a little bit. If we take multiple thinner pieces of metal and we laminate them together, each one will have a very small eddy current, but it will be much more efficient at passing the magnetic field than if we had one solid piece. So that's why you see these laminated pieces instead of one solid chunk of metal. So we have the losses that we get through eddy currents, and we minimize those by using these laminated plates, and they have these, they're also coated in enamel to kind of give them a little bit of separation. And that eddy current loss is minimized, but it's still there. So that's one of the losses that we have when we use a transformer like this. And then the other one that we're going to talk about is reluctance and permeability and how they interact. let's talk a little bit about the core of the transformer, the part that takes the electrical energy and transfers it as magnetic energy so that a transformer can function. Now, this is very special, the type of metal they use. And depending on the application, the formula used in this metal can be different. So high frequency transformers will have different compositions of metals than transformers that work at mains frequency, which is either going to be 50 or 60 hertz. That's very low frequency. Transformers used in radio circuits can be in the many tens or hundreds of megahertz and will require a very different type of metal. Why is that? Well, let's talk about the most basic thing in this, and that is the word reluctance. What is reluctance? Well, magnetic reluctance, or we could call it magnetic resistance, I guess. It's defined as the opposition offered by a magnetic circuit to the production of magnetic flux. Magnetic flux is the flow of that magnetic field. So just like current flows through wires, magnetism will flow through this core. And as I said earlier in the video, this metal doesn't like to change the way it is. Whatever state it's in magnetically, it wants to stay there. And to change it, you have to put a little bit of energy into it to get it to change. And there will be a delay from when you increase, for instance, when we go from 0 volts to 10 volts, there's going to be a delay from when that transformer is non-magnetic up into when it magnetizes to the level that it would be at 10 volts. There's a delay there. And it's going to, for that period of time, it's going to resist that. We call that reluctance. And since we're using AC, that's constantly happening. It's changing up and down, up and down, up and down. So that reluctance can really eat up a lot of your efficiency of the transformer. Now, just as the reluctance kind of controls how quickly this can magnetize and demagnetize or change its magnetic field and direction, also there's another factor called permeability. Permeability is, once it gets up there, how much magnetic energy can it store? Different materials magnetize at different total amounts depending on how much energy you put into them. Now here's the thing. Permeability and reluctance kind of affect one another. So what you'll find out is really high frequency transformers will have a type of metal that can change. Its reluctance is very low. It can change very quickly from one magnetic state to another, but it's not very magnetic. In other words, it doesn't do a good job of getting very high magnetic density to it. Whereas this type of metal that they're using in here, these plates, they're very efficient at getting magnetized, but they just take a longer time to do it. So as I said, nothing's free in this world. So it's a trade-off. So the higher the permeability it's going to have, the more reluctance it's going to have, and vice versa. Because this is low frequency, it's only 60 hertz that we're putting in here, or 50 hertz, that's not a problem. So we like having the huge amount of density. That's how this small of a transformer can deliver so much current and so much wattage from one side to the other, if that makes sense. However, if we tried to put anything that was real high frequency, you know, in the hundreds of kilohertz, or even in some of the tens of kilohertz, it would never be able to magnify or magnetize to its highest potential because it's taking too long, and by the time it starts to magnetize, your AC waveform's already dropping and reversing the other direction. So you really won't have a good account of that magnetic field building and collapsing, that changing field that you need for that inductance to take place between the primary and the secondary. Does that make sense? So you have to use the correct material of your transformer based on the application of the transformer. And that's what really controls the size of the transformer and the metallic formula and even its properties. So there are data sheets that you can get for transformers. Now this one, who knows, it came from China or someplace. You might be able to find a data sheet, maybe not. But some of the bigger companies that manufacture them have very detailed data sheets, and they get into great detail about all these things and how it works. Now, I'm not going to get too much more into how the transformer works because this is only 101 and a half. There's a lot more information out there about transformers and how they work and how you implement them. But the main thing I want from this video is just so you understand the idea of what a step-up versus a step-down transformer is, how the input and output wattage have to be balanced, and you have to take into account the losses of the transformer, that a transformer needs a changing magnetic field in order to work. So if we put DC on here, you'd have one little pulse that would come out of here, and then once this comes to rest, there would be no more transfer of energy from this coil to this coil. So if that makes sense. So you need to know that. When we pick the transformer for the application, we kind of need to know the total amount of wattage that the circuit's going to draw, and then we have to make sure that the output of the transformer matches that. And we can use all those techniques that we just showed in this video to do that. So we determined from this video that this transformer is the correct one for that circuit, and that it should run relatively cool, and it should be efficient, and it should be able to supply more than adequate power to that amplifier. Because remember, this is just going to be a 10 watt to 12 watt amplifier at the most. And you're probably not going to run it continuous 10 watts because it'll have a lot of distortion. If you look at least with the 6AQ5, and it could be a little different with the 6N1 or 6P1, I'm sorry. But if you look at that 10 watts, it's 5% distortion. So I doubt you're going to run this thing at a continuous 10 watts. That being said, you probably could get 10 watt peaks at low distortion. I don't know. We'll test all that when we build the amp.